Yeah. Now, this is called as dynamic shear rheometer. So, as we know, the rheology plays a very important role in the bitumen characterization. So, this dynamic shear rheometer will give different kinds of rheological properties. It can be viscosity, it can be complex shear modulus, phase angle, then creep and recovery studies, and stress relaxation studies. So, these kind of properties will indicate the bitumen properties in the short term and in the long term also. How it will behave in the over time for different frequencies, different temperature. So this can simulate all these conditions in this particular dynamic shear rheometer. So but this is it is only the bitumen, not the mix. So in this study only the bitumen properties, not the mixture properties, right? So basically this consists of a this basically operated pneumatically. So pneumatically means it will operate through pressurized gas. This is a pressurized gas cylinder. So this is applied to this particular DSR. Now with this dynamic shear will apply the load, right? And this is the movable element. This moves up and down. Now in this particular point, we will fix a spindle. Now this particular plate is 25 mm in diameter. Now this is basically used to study the bitumen which is RTFO aged and unaged bitumen. So in this case we go for 25 mm diameter plate. Similarly, this is the this both things form the parallel plate system. So this plate is fixed and this plate which is attached to the motor, this will rotate, right? This will rotate like this and supplies the shear force. So when it rotates on the bitumen this particular point, when this rotates, right? So it applies shear force. Now by this shear force, it will measure different properties. It can be the resistance, it can be the viscosity and phase angle. All these are measured with this particular setup. Similarly, if you go for a PAVH bitumen, right? So what we will do? We will reduce the diameter to 8 mm because in PAVH bitumen, if a thicker, bigger sample, it can undergo breaking since it is very stiff. So what we do? We reduce the size to 8 mm diameter and also the spindle diameter will be 8 mm and sample thickness will be 2 mm and in this case it will be 1 mm sample thickness. So we will see how it is operated and how it is fixed, right? So first what we will do? Before starting, we will run this software which is called as RSpace. Now this is made by a company called Malvan. The brand company is Malvan. The brand name is Canexus, right? So other than bitumen, we can study the properties of different any fluid. It can be a shampoo, it can be a gel, it can be any fluid, right? Which has viscoelastic properties. So bitumen is used in different industries. It can be food industries, chemical industries. Then it can be in bitumen refineries, right? So now we will start this. So now when you open this particular equipment, first thing is that it asks that please ensure the all hoods and accessories are moved away from the particular equipment. So what hood means? This is a hood, right? So this particular thing is called as hood. So it is movable. This is called as hood and here we will fit the spindles. So all these things should be first removed, right? Then what we will do? We will press the next button. It is moving upwards. It's going to the position, some particular position. Yeah. So now basically what we will do? First we will zero gap. Now zero gap means we will calibrate the equipment to zero gap. So first we will fix this particular 25 mm plate, right? You see here, you just hold this plate and you can press it. It's a lock, press lock. When you press it, it gets locked. To open the lock, just hold it and leave it. So you just push it, right? You push it, it gets locked. To open this, you can just press this button, this one, and you can just pull it down. So this way, we will press it, now it's locked. So we will keep this bottom plate also, this parallel plate. Here, you can see 3 hooks, right? Here, these 3 hooks. These hooks will go in the hole here. And here there is a lock. So we will lock this particular position. so it won't move further, right? So now what we will do, once you do this, you have placed this particular geometry, right? The current geometry it is saying that PU 25. 25 indicates diameter, right? Next, okay. Next. So now it says that open the active hood, right? Ready to 0 geometry. Now what 0 means what happens? This lower plate, this upper plate, this particular upper plate will completely come to the lower point, right? So we'll see what will how it is done. So you can see when I press next, says the instrument is about to 0. Ensure that any sample is removed and click next to perform. While zeroing, what happens? You should remove any sample, right? You remove all the samples, and then you have to remove the hood also. This hood should be removed, separated. And then you will press next. You can see here it is coming nearby. It is going to come to the 0 point. Now it is completely touched, right? Now this is the 0. So now the 0 has been done. So now it is sitting on a target gap of 70 mm. You can see here this particular gap. This is number is 70 mm gap is there, and temperature is 25 degrees, right? So now what we will do? We will load a sample, right? We load a sample and run a test. So now what we will do? We load the sample in the parallel plate. So you can see the choose material. So you can see description VG30. First we will test VG30, right? So next it asks for what gap you want to maintain. Normally for DSR we maintain 1 mm gap, right? In the case of unaged bitumen. So we will place 1 mm gap, right? Yeah. So it says open the active hood. Now the hood is open here. Then this is asking that open the active hood for ready for loading sample. This step will repeat until the hood is fully open. Next. So now we will load the sample. Now this is the bitumen sample. Now this is a bitumen VG30 sample. Now this can either be used the silicon mold to prepare a sample, or you can prepare by hand also. Normally we will take this kind of ball, we will prepare a ball shape and we will place on the bottom plate, right? So this is how we have kept. We will keep an excess amount so that we will trim it later. So what happens when this will press the bitumen and we maintain this 1 mm gap, some amount will ooze out or come out. Now that amount will be scraped with the scraper, and there will be some small amount of bulging, right, of the sample. It should not be a concave, this surface, it should be a convex surface. So it is a bulging is required site. Next, here it is slowly coming down, but you can see how it presses, right? You can see how it is oozing out the bitumen. Trim this sample. It's asking is sample trim. So once you trim the sample, so press S to continue loading, right? We'll press yes. So it will continue to 1 mm, right? Now we'll close the active hood. So why do we close the hood? To maintain temperature. So this particular hood is closed now. This will close it, right? Now it is closed. Press next. Now this particular sequence is completed. That is the loading sample completed. Now this is now the temperature is 60 degrees, right? 60.72 is running. So we are set for 60 degrees. So we'll set for 60. Now what we will do, we will run an oscillation test. If you see here, the gap is 1 mm, the temperature is 60 degrees, right? This temperature we will study the will do oscillation test where we will determine the phase angle and the complex shear modulus for a given bitumen. In this case, we are testing VG30 bitumen, right? So what we will do, we will run a using constant shear strain mode. We will apply a shear strain of 10%, right? Now recommended is 9 to 12% is recommended. We will apply at 10%. Now the frequency should be 10 radians per second. Now this corresponds to approximately 90 km per hour. So this should be 1.59 Hz. That is 10 radians per second is equal to 1.59 Hz. Now when you press next, start running the experiment. So you can see here the values in this particular. The complex shear modulus is how it is changing. This is the live data. This is the change you can see. You can see the phase angle here. The green is the phase angle. Now this blue is loss modulus and the red is the storage modulus. So we will see in theory class that the complex modulus has two components. One is the loss modulus, other is storage modulus. So if you see live data, this is data what is being capturing. So the complex shear modulus is 345 pascals, right? And the phase angle is what is being shown here is around 85 degrees phase angle, right? So now what we will do, we will unload the sample after test is completed. So once you, here you can see a button called unload sample. When you press this, it will ask you to first open the active hood. Why? Because spindle will move upwards now. When you press next, the spindle moves up. You can see this spindle is moving. So when it goes 70 mm gap, it will stop. Now we need to clean this particular setup. Yeah, good afternoon all. So yesterday we did testing on bitumen, right, using dynamic shear diometer. So basically we did oscillation test to determine G star and the phase angle. So what happens in this test, basically you have a parallel plate arrangement. This is a plate which is fixed to the motor. This is a bottom plate which is fixed, right? This is movable and this is fixed. So in this particular thing, we placed a bitumen, right? We placed a bitumen, the gap of 1 mm. Thickness of bitumen was 1 mm and diameter was 25 mm. So what happens in this, basically, to apply oscillations such that, let's say at the B point, right, the 0 point. So now the spindle moves to A and comes back to again B. Again from B, it goes to C and comes back to B. It is one cycle. This is the waveform here. Let's say it starts from B, right, it goes to A, from A it goes to B, again from B it goes to C, and again from C it goes to B. So this is one cycle. Now this cycle we apply at a frequency of 1.59 Hz, 59 Hz or 10 radians per second. This is the frequency what we will apply. So and then we determine two important properties of bitumen. One is G star, it's called complex shear modulus, and then the phase angle. The phase angle is a time lag between the stress and the strain. So we will talk about more this in theory classes. So this can be determined using the oscillation test. So we will see the results of the bitumen what we studied on this test. So we studied three bitumen. One is VG30 and CRMA 55 and PG82 minus 10. So we will see how the values of the three bitumen we got and how they compare after RTFO aging, right? Now these are the results of the testing oscillation what we did for the three bitumen, VG30, then CRM 55, then PG82 minus 10. So if you see, we have derived basically four values. One is G star, then storage modulus, loss modulus and the phase angle, right? The G star is expressed in pascals, right? And this particular phase angle is expressed in degrees. So basically the complex shear modulus is a stiffness component, right? It indicates how stiff is the bitumen, and the phase angle will indicate, right, the state of the bitumen. Is it elastic state or the viscous state? If phase angle is too high, then it's a viscous state. If it is too low, it's in the elastic state. So now if we compare this values of the three bitumen, right, between aged, unaged and aged conditions, so we will see in the graph format, so for better understanding. So now you can see the first graph is complex shear modulus versus different binder bitumen type or binder type. Now if you see for VG30 and VG30 unaged, you can see how this stiffness has increased. So in this unaged condition, the modulus was something around 3300, but after RTF aging or short-term aging, you can see how much increase in the stiffness or the complex shear modulus. Similarly, if you see CRMB, the modulus was around 2000. After aging, that is short-term aging, it is around 4000. If you see PG 8210, even before aging, right, in the unaged condition, it is very stiff. It's a very stiff bitumen, right? So we'll see how this grading is done, right, on what basis in the theory classes. Similarly, if you see the face angle, now for VG30 in the unaged condition, it was something 85. So after aging, it is 80. So as we age the bitumen, it becomes more stiff. That means the viscous component decreases and it becomes more stiffer, right? Similarly, if you see CRMB 55 also, it was around 85, and then for aged it become 82 degrees. But if you see here, this particular PG 8210, it's around 68 degrees in the unaged condition, right? So if we age, it can reduce much more, right? So this way, this particular dynamic shear emitter can be used to determine the rheological properties like complex shear modulus, face angle, and much more other properties which we'll study in the theory classes, and grade the bitumen depending on the performance, right? We call it PG grading, what's called performance grading. So we'll see how it is done in the theory classes once again, and this is how the test is basically done, and this test is used to further grade the bitumen, right? How we grade the bitumen through viscosity and penetration. So as per SuperPave, we will grade the bitumen using these particular properties. One is G star and sin delta, right? For a given temperature, fixing the performance properties.